Hello and welcome back. This is a table that I think every designer should have in front of him or herself when doing design. This is, and in fact, a more complete version of this table is what you really want. What this is a listing of energy per micro operation for different samples of micro operations. This is collected from the literature, or largely calculated, and in fact is taken from one of our own research projects where we're building such a table. In that particular research project, we're aiming to look at energy efficient computation at the 7 nanometer node. Hence I've got the 7 nanometer table on the right here, which is kind of useful in this table since the examples that I've taken are taken from different technology nodes. Why don't you take a moment to look over this? Possibly even pause the video and absorb some of it in. What you'll notice is that these numbers vary enormously. Right? What might surprise you is possibly the most efficient aspect here is doing a complete multiply accumulate, a 32-bit multiply accumulate. That is a multiply and an add and a store. This is this has been demonstrated in a 32 nanometer node and not at a bit under 20 picojoules per op. In contrast, moving the same 32-bit data to or from a DDR DRAM takes 4.8 nanojoules, right? More than 500 times more, 500 times. It might even surprise you that as you go from a fairly substantial arithmetic unit, a multiply accumulator, to a complete CPU core, that actually has a much higher energy per operation due to all the overhead functions that go into building a CPU core over just the multiply accumulate. Looking at some of the others here, it might surprise you that most of the energy in this DDR3 memory operation does not go into the actual store or read from the actual DRAM bank. That can be done relatively efficiently, but not as efficiently as this multiply accumulate. Most of the rest of this energy is in the overhead of moving the data to and from. SRAMs, on-chip SRAMs, in particular caches here, are better than off-chip DRAMs. In fact, because this is just the DRAM bank, it's comparable at least in this structure. But since most DRAMs are off-chip, they're going to be worse than on-chip SRAMs. Even a pipeline register or a register file is a significant proportion of the multiply accumulate. Here's a scaled figure to normalize it to one node. A pipeline register is a significant proportion of the total in the multiply accumulate. An STT-RAM refers to a new emerging type of memory called a spin torque transfer memory, and this is in here because it's from the original table. Don't worry about too much for the purposes of this class. Moving data off chip is very computationally expensive. A research grade, very low power, high speed I/O system still takes about 37 picojoules per word. Compared with moving it halfway across a chip, is only 8.7 picojoules. And since a lot of our work is in 3D chip stacking, and I'll explain this in a moment, I want to show you here that moving data vertically within a chip stack can be more efficient than either of these above. You'll notice that moving the data off chip is much more expensive energetically than doing a very complex calculation. So there's actually dramatic differerences in terms of how you organize your data, how you organize your data flow, how you structure your design, and what algorithm you use even, that can make a huge difference on power consumption if you consider these sorts of issues, and possibly you can do some enabling calculations while doing design. And frankly, I'd encourage you, if you're working in a power constrained environment, to develop a table like this and actually use it while you're doing design. And again, this is exactly what we do in our research work on low power logic. Here I'm illustrating some of these issues in a different way. Looking at some different issues actually. Here is an exemplar power distribution for a chip. I've actually forgotten which. What you'll see here is, again, logic is not the majority of the power. What's the single biggest consumer of power on this chip? It's the clock. The clock toggles every clock cycle, and it goes to each and every register. So it has a fairly large capacitive load as well. Thus, the clock typically takes between 20 and 40% of the total power. Adding registers to a design not only increase the power consumption due to the internal operation of those flip-flops, but also add to the clock load, increasing the power needed to distribute the clock. Frankly, there's a good argument for absolutely minimizing the number of registers needed in a design to those simply needed for the logic function of preserving data between clock cycles. And this is one of the reasons, because of clock distribution. What's the next biggest consumer of power here? Well, it's on-chip interconnect. It's very comparable to logic in this example, but it's a very significant proportion, and a surprising significant proportion. And again, all of this stuff around here is not functional. It doesn't add to completeness of the task. It's necessary, and it's hard to avoid, but it doesn't add to completion of the task. It's logic and memory that actually does the task that you need to do. So again, you'll notice that the long lines on the chip, including their internal repeaters to keep their speed up, are significant portions of the total power, as are the local lines. And architectures that minimize the amount of long-range interconnect or its usage on a chip do save significant power compared with architectures that spread the data all over the chip over and over again. Here you see logic and leakage power. This I don't remember the technology node this was in, but the leakage power will get worse and worse as you go to transistor scaling. At 22 nanometer and below, it will be a much bigger percentage of the pie than is shown here. And here's the on-chip memory, the on-chip SRAMs. In memory, because it's dense, it tends to have a lot of leakage power, and again, that percentage gets bigger and bigger as we scale technology. So one thing I talked about a slide back, and also impacts the discussion on the previous slide, is the use of 3D IC technologies. The idea here is you can make two chips face to face. These are the silicon plus interconnect layers. This is the CMOS wafer underneath. You can make two chips face to face at a very tight pitch and have a very low power interface vertically. You can then bring out the I/O and the power and ground delivery through what are called TSVs, or through silicon vias, through to your bumps that go to your packaging. You can mount chips back to back and back to front as well, using a combination of micro bumps and through silicon vias. Now the points of these are multifold. First of all, you can have different technologies in the different layers that can lead to further power optimizations. Secondly, it takes very little power to transfer data between these chip faces, and through intelligent design you can exploit that. Thirdly, if you take a large chip and build it as a two-chip stack like this, then the power taken by your clock will go down somewhat because your clock traces will be smaller. Number of registers won't change, but the clock traces will be smaller. And certainly your global interconnect power will go down because your long lines will be shorter. All these things through intelligent design can lead to significant power advantages in using 3D technologies. In fact, a big part of my current research in my group is working out unique ways to exploit 3D to get improvements in energy efficiency of 30% or more. Next, I want to talk a little bit about how you can estimate power through the computer-aided design tools. Quite simply, after place and route, the tools can tell you the capacitance per node. You as the designer know VDD and F, and of course VDD is set by the standard cell design as well. So the question is, how do you calculate N switch per node? One method, and it's fairly quick and simple and easy, is to just assume a fixed N switch per node for each node to get a rough estimate of power consumption. And in fact, there are tools that support this. The nice thing here is this is quite a quick and easy calculation, but it's wrong. Because any estimate of N switch is going to be out. In fact, the tools that do this tend to use an N switch of around 50%, and thus will overestimate power. However, for comparative calculations, this still can be quite useful. To get power accurately, at least for a specific workload, you actually have to run the logic simulator, use that to extract N switch per node, interpolating that for nodes that are not in the RTL, and then back annotate that to a power calculator. And there are tool flows that support this as well. So through these methods, you could actually directly calculate the power consumed in your design, and actually even play what-if games with the RTL in order to minimize the power. But again, good design defeats analysis. If you design thinking through a table like this, having in front of you while you're doing design, then you'll be a lot better off than just trying to do it through simulation experiments. But nonetheless, this is very useful, and it's used in practice in order to understand and predict the power consumption of a design. So this brings me to reducing power through smart design. In the first module, we talked about clock gating and dynamic voltage and frequency scaling. These are all kind of system level ways to reduce power in certain scenarios that are not necessarily available to the RTL designer. They're often done at the system level. There are major blocks have their voltage turned down, or major blocks have their gates clocked. The logic designer can't influence it a lot. So the question is, what can you do as a detailed logic designer that will improve power efficiency or energy efficiency? Well, one, of course, is to use algorithms that require fewer high energy micro-operations. For example, signal processing algorithms that require fewer multiplications or narrower multiplications. Do you really need 32-bit arithmetic? Can you get away with 20-bit arithmetic? Can you get away with an integer multiply and tracking the exponent rather than do full floating point? A big one is, can you keep the data on chip, avoiding expensive DRAM accesses even at the expense of more SRAM accesses on chip? That's early in the design. Later in the design, you want to be thinking about what are the micro operations that take high energy, and think about avoiding them. For example, use muxes instead of arithmetic units and shift units, etc. A big one is reduce the number of registers. Don't have unnecessary registers if your target is low power design. And of course, reducing the number of memory accesses, whether it's SRAM or DRAM, can make a big difference. Thirdly, don't be wasteful. If you have a logic unit that through some aspect of the design is toggling and you're not using the result, then that is wasted power. And this scenario is actually quite easy to do accidentally, and I'll show you some examples in a moment. So you as a designer might even have to add features to prevent wasted toggling and wasted power consumption. Remember, your goal here is that each logic toggle in your design is contributing directly to the end computation that's required. A good example here is if you have combinational logic units, large ones such as say a multiplier. Remember, if the inputs change, the module reevaluates whether you actually use that output or not. Finally, there are synthesis tools and options within the synthesis tools that focus on minimizing power rather than minimizing area. And these can make useful differences in the end power consumption. So next I want to look at this concept of useless toggling and illustrate through some simple examples. So here I've written some code that's quite straightforward and quite natural to write. If C is high, D equals A plus B, else D equals A. It's quite fine, and you think it'd be fine. Well, what that building is the unit on the right here. D's a flip-flop because it's assigned in a pos-edge clock statement. Have a mux. We have an adder to one input of this mux, and A to the other input of this mux. Note that whenever A or B changes, this adder reevaluates no matter what. A and B just connect to the combinational inputs. Whenever they change, the adder will reevaluate. And this is true whether C is high or not. If C is low and A and B change, then that's wasted power. Well, there's several possible ways to fix this. One would be to have this alternative send C to an input mux to this adder to present zero adder when C is low. Here you still get one transition. When C changes, you'll still get one transition because you'll be going from adding A and B to adding 0 and 0, so you still get one complete set of transitions, but you use less power. There are other techniques where you could possibly put a register on the input of this adder rather than at its output, or as well as at its output. This possibly consumes more power if C is changing a lot, but could be quite efficient in other scenarios. So here's that example with a mux to 0 at the inputs. Notice it's different code, it's different RTO. But if C is low for long periods of time, this would be a very efficient design, possibly more efficient than adding a register at the inputs to the adder. So I've done this by explicitly building these muxes at the input of the adder, controlled by C. The other high activity units, a multiplier is a big one, a very big one actually. And again, one alternative when considering a multiplier, a high activity unit in a scenario to prevent, like the previous couple pages, in order to prevent wasted toggling, would be to register its inputs. Here what I'm doing is, what I'm illustrating on this bottom right here, I've got two inputs to the multiplier. If B is low, I want to use the result, and I'm going to multiply whatever these two inputs are. When B is high, I switch to the output of this register, which essentially freezes the input to the multiplier to whatever was there on the previous clock cycle. And this is assuming I don't want whatever comes in here to be multiplied. And this could save quite a bit of power at the expense of these additional registers. So this is particularly useful if B changes a lot. If B was a low activity factor, the switching to the zeros might be lower. How to decide these things? Well, again, a table like I have on the first page could lead to detailed guidance on how to choose these alternatives. You'll see some exercises around scenarios like this in the quizzes associated with this section. So again, here's my commentary here. Remember this in this example here, the energy in the multiplier is wasted if B does not change. Switching the muxes to the inputs and providing this additional register to freeze the inputs when B is saying we don't want the result of the multiplier can save a lot of power compared with the version on the left. And again, what we're doing here is the multipliers are essentially freezing the logic to prevent useless toggling. So that brings us to the end of this second submodule and the end of the low power section. I remind you that it's very useful to have some understanding of the relative energy per microoperation for different things you can put into a data path and controller. As a general rule, DRAM access takes more energy than SRAM access, it takes more energy than arithmetic, then it takes more energy than a register. Your goal is really to minimize the number of microoperations required to complete the task and try to get it down to those that are only required to complete the task and remove microoperations that are simply there to frankly, to speed it up. The trade-off here is that you might, for example, not pipeline a design in order to reduce its energy per operation, which means, unfortunately, that it will be slower as well. So there is some penalty to doing this. You might be slowing the design down, reducing the amount of microparallelism in order to reduce the energy per operation. Also, I remind you, in terms of data communications, off-chip is worse than on-chip, which is worse than the 3D if that's a technology that's accessible to you. And the goal is really to minimize energy per operation or complete task via a good design. Those algorithms that minimize higher energy operations, logic and control structures that minimize overhead operations. If your goal is to be energy efficient, then, for example, don't add pipeline registers. It will slow things down, but you'll be a more energy efficient operation. And of course, very importantly, remove wasted power. And again, there's very specific examples of complex combinational units that consume a lot of energy when the inputs change. You want to make sure they're only computing values you're actually interested in. If you're not interested in those values, then somehow freeze the input to that high activity unit in order to prevent wasted power. Okay, this again was a very important set of notes, increasingly important as we enter the power-constrained era of logic design. And thank you very much for your attention.